Good morning, everyone. My name is Anwar Fayed. I'm a member of NICIS, and it's my honor to open and chair this session concerning scientific workflows. And I'm also privileged to introduce our keynote speaker, Professor Deelman. I'll just briefly read the bio. Professor Deelman received a PhD in computer science from the Rensselaer Polytechnic Institute in 1998. She then joined the University of Southern California Information Sciences Institute, and she is the leading science automation technologies group. She's also a research professor at the USC Computer Science Department and a AAAS and IEEE Fellow. So Professor Deelman is also the founder of the annual workshop on workflows in support of large science, which is held annually in conjunction with the SC conference. And in 2015, Professor Deelman received the HPDC Achievement Award for contribution to the area of scientific workflows. And in 2022, she received the Europar Achievement Award for outstanding contributions to parallel computing. So it's my privilege and honor to introduce Professor Deelman. Thank you.
Thank you very much, Anwar, for this kind introduction. Looks like my slides are going. And I also would like to thank Happy and Werner for having me here at this conference. It's really a pleasure to be here. It's my first time in South Africa and first time on the continent, so it's a very special experience. Also, just being at this conference has been very rewarding and interesting. I really appreciated the poster session yesterday where I got to meet a lot of the researchers here talking about their work, and it was great to see and learn about how they're using CHPC for their work. So today I would like to talk about scientific workflows and how the workflows have changed over time, how the applications have developed over time, and how the workflows had to move along with them to be able to enable them to execute on a variety of cyber infrastructures. And so in particular, I'll focus on the Pegasus workflow management system and how it also evolved with the times. In my talk, I'll mention 5 principles that really helped us move with applications and with the cyber infrastructure, and then talk about how we see the future coming along. So we all know that we live in a very heterogeneous world. So we have very heterogeneous applications. The resources that these applications execute on are heterogeneous. Our users that have access to the resources and the need to run the applications are very heterogeneous as well. So for example, if we look at the users, there are some that come from a very large collaborations, such as SKA. And these users normally have cyber infrastructure experts that are embedded within the large collaborations, and they're there to develop the cyber infrastructure and also to help the users utilize the infrastructure for the science. Then you have medium-sized groups where you have maybe several PIs getting together to solve a particular problem. So you can think of a EHT, which is the Event Horizon Telescope collaboration, where you have several PIs or a number of PIs in a collaboration working together on a particular topic. They usually are domain scientists, but they have also experts maybe coming from the domain, but with cyber infrastructure expertise so that they can develop new technologies, new applications, and leverage cyber infrastructure. Then you have individual PIs, which are, for example, you can imagine somebody with a DNA sequencing machine, and they collect large amounts of data, and they need to analyze it using a variety of resources. So their knowledge of cyber infrastructure may be lower. And then obviously you have educators and students and also the broader public that we are looking for push button solutions, on the iPads or on the phones, looking at how we can understand and contribute to the scientific process. So at the same time that we have these heterogeneous users, we have a variety of different applications. They're mostly non-monolithic. They're a mix of single core or multiple core applications. They can be parallel distributed. They're written in a variety of different languages. They have task dependencies. They have data dependencies within them. They could be iterative, and also they can access instruments and collect large amounts of data, and also model various systems. So think of machine learning applications that are now consuming large amounts of data to develop the models. And then we have the heterogeneous resources that all these applications run on. So we have sensors, we have phones, you have a variety of instruments that are deployed in the environment. You have edge devices that are now very present in a number of situations. And then all the way up to clouds, big data centers, and high performance computing resources. So having that, how do you then tie it all together? How do you enable science to happen for the users with the infrastructure that's available, with the applications that they need to run? So this is something that was actually talked about yesterday, about how do you democratize access to the cyber infrastructure, enable science at scale. So we started working on that back in 2000 and 2001. In 2001, I visited the Virgo instrument in Italy. So this is a laser interferometer gravitational wave observatory that you see the instrument in the middle. You have the two long arms that are 2 kilometers long, the masses suspended in these arms, and lasers look at these masses and see if there is a gravitational wave passing by. So there are small deflections, distortions in the masses. You can think that potentially that's a gravitational wave. So back then we started thinking about how we enable these applications to run across the variety of resources. In particular, we're working with LIGO in the US. So this is the counterpart to the Virgo experiment. And they had two instruments in the United States, one in Louisiana and one in Washington State. They had data centers that were attached to the instruments to collect and store the data. But then the data was distributed in the environment. And also, and I think my mic died. In the environment, and also you had the computing being distributed across various resources as well. So by nature, we're working in this distributed data and computation environment. At the same time, we're exploring issues from the computer science side and looking at developing a model, which we called the virtual data grid, where a user could come to the system and they could ask for particular data without worrying whether the data was already available somewhere, already pre-computed, or whether the system actually needed to take the raw data and generate the necessary results. So in this scenario, LIGO scientists would come to the system and they'd ask to conduct a pulsar search on the data that was collected during a particular time frame. So the system then needed to understand the request. It needed to determine whether this data was already available somewhere. And if not, it needed to plan the data movements, the computations to generate this data for the users. So we started working on making this virtual data grid a reality. In particular, we developed a web interface where the scientists could go in and put in the metadata about the request, which instrument they wanted to look at, and the timestamps and so forth. And then we used AI planning techniques at the time, which were actually pretty primitive and didn't work particularly well, but we're able to generate these simple workflows that you see on the right, which would take data from the archive, it would clean it, it would make longer duration timeframes out of the shorter periods, it would generate this time frequency image, and it would look for the gravitational wave signal in that image. And so in 2002, we did a demonstration at supercomputing. We had a nice visualization that you see right here of looking at pulsars on the sky. And we had the system that you see on the right. It was pretty primitive, but it was taking this request coming from the scientist. It was developing a directed acyclic graph showing what needed to be done. And then it used Condor Dagman, which is a workflow engine, to execute the computations across the various data and compute systems that were available to LIGO. So we were very proud of our accomplishment. We showed it to the LIGO collaboration. And what it turned out is they really didn't like what you see on the left, which is gone now, but what they really liked is this idea of a workflow that you see on the right. So they wanted to manipulate these workflows, these graphs directly and change them around, substitute components and so forth. So our lesson learned out of this experience was that working with scientists is very rewarding. Working on real life problems is really interesting. However, you really need to listen to what the scientists need. So in our case, we're very excited as computer scientists about this virtual data paradigm and what it could allow us to do. However, that was too abstract for our users. However, the things that they still needed to do, so they needed to deal with these distributed environments that were heterogeneous, and they needed the separation between the workflow description and the workflow execution. But that first abstract description couldn't be as abstract as we had at the beginning. So then our focus then became on request planning and scheduling, so taking a workflow that's abstract and refining it to something that's executable, and also looking at the robust execution of these workflows in a variety of environments. So Pegasus is to be a workflow management system that automates complex multi-step processing pipelines. It enables both parallel and distributed computations. It automatically executes the data transfer, so it moves the data on behalf of the users. It records how the data was produced, so it keeps track of provenance. It handles failures in various ways, and it also keeps track of low-level details and where the files are placed in the environment. So if we look back to what happened to LIGO, so in 2006, LIGO was running using Pegasus on the Open Science Grid, which is a distributed infrastructure in the US, composed of a number of different clusters. And this shows basically a graph of the computations over periods of days. And then 16 years later, so we're looking at now 2022, along the way in 2016, they did the first detection of a collision of two black holes using Pegasus, so using the workflow technologies. They were able to do the calculations that confirmed this first detection. In 2017, 3 LIGO scientists have received the Nobel Prize for the work. And also the LIGO scientists had seen the first multi-messenger neutral star merger observation, which also was seen by other telescopes as well. So one thing that you can take away from this image is that it really takes a lot of time and a lot of investment and collaborations to really get to these important results. If we look at also how things have changed since 2006, when LIGO was running on the Open Science Grid, at that time we're in the teraflop scale. So we were writing papers about the teragrid in the US. On the top 500 list, the DOE's Lawrence Livermore IBM Blue Gene was the top machine. Today, 16 years later, we are in the exaflop scale. So we have the new machine at Oak Ridge that has passed that benchmark in May. So you can see that things have changed quite a bit over time. And yet we need to be able to support scientists that have pretty much the same or similar analysis that they want to run, maybe enhance in a certain way. But basically, they want to be able to reuse a lot of the components that they had before in their work. So one of the principles that we employed to be able to support that was to provide resource-independent specifications of workflows in Pegasus. So the user basically describes the workflow in terms of computations that we want to do. So they can say we want to do an FFT on a particular file, but they don't talk about where that FFT is going to be executed, where the code is located. They don't talk about where the file is located. This really deals with abstract space, the logical space, where then the system does the mapping from the logical to the physical. And when Pegasus does the mapping from this abstract workflow to an executable workflow that you see on the right, it adds nodes to the workflow to stage data in and out of the computations. It also adds nodes to stage data between various compute sites if there is a need. It cleans up the data, and I'll talk a little bit more about that. And also it stages data out to where the user wants it to land in the final portion of a workflow. And also it can register the data in catalog, so you can keep track of what's happened. So this type of resource independent specification has helped a number of applications over the years. One of them is the CyberShock application out of a Southern California earthquake center. So this application basically generates high seismic hazard maps of Southern California and now Northern California as well. And it tells you what kind of ground motion you can expect within a particular geographic location over a period of 50 years. So you can imagine this helps civil engineers determine to what tolerances they need to build the structures. So the SCEC applications are a mix of MPI and high throughput computing jobs. And they used the various machines of NSF, both high performance computing and high throughput computing in 2006. Today, they're using the basically similar codes enhanced in certain ways, but they're using them at scale on the today's systems without changing the overall structure of the computations, without doing a lot of revalidation. So the same workflow could work as they worked before they can work today. So another principle that we have is the notion of submit locally and run globally. So oftentimes, if scientists are running over periods of days, you cannot imagine them putting a workflow management system on that particular resource that they're running on, because resources come up and down, and you don't want to have your whole work destroyed by the various either maintenance or failures and so forth. So you really want to put the workflow management system outside of where your execution environment is. So we call this a submit host. This is under the control of a user. It could be your laptop. It could be a community machine that's maintained, for example, by LIGO. And from there, the system orchestrates the computations across the various resources. It moves the data to the resources where the computation is taking place. And so in our model, we can model different compute sites. We also separate the data modeling into the input data sites, the staging data sites, and the output data sites, so that we can mix and match the various configurations. And then, so the idea is that you deploy Pegasus, and it can then submit jobs to these various resources. It coordinates the data movement, and it can do various optimizations depending on where the computations are taking place. And I can talk a little bit about it later as well. So the idea is that you can do these cross-site computations, and this is being used quite heavily by scientists out of Vermont that have an integrated assessment modeling system for the lakes in that area. They're looking at issues of modeling land use, watershed, looking at governance, economics of the whole system. And they're using resources both at University of Vermont, but also at high performance computing systems at UCAR. Again, they don't need to change their workflows to do so because we have this idea of portable workflows, so workflows that are abstract, so they can go into any type of target execution sites, and also the notion that you can spread the work from a submit host to others. So another application that of these two principles really helped us with was when cloud started to come online. And in 2008, we basically didn't have to do many changes to Pegasus in order to be able to run our applications on these cloud environments. And so this is an astronomy application. You see the result on the bottom. And on the right, you see a particular workflow for that application. This is out of Caltech. And at that time, we're using this application to determine what are the different costs and also overheads associated with cloud computing. And so with the simple principles of this abstraction and also the separation of the execution and where the computations take place, we're able to move to the cloud. The other things that also helped us with that, though, so principle number 3 is we support flexible data staging configurations. So you can have, for example, you can use Condor.io that takes data that's at the submit host, so you can have storage associated with that submit host, and you can stage the data from there to the resources that are available to the scientist. And the obvious limitations to that because you have just the input data is a particular location. We in the non-shared file system, so we can also use the Pegasus data transfer mechanisms that I'll talk about in a minute. You can also move the data around more flexibly from an input data staging site that's not collocated in anything. So you can think of Amazon S3 bucket, for example, move it into where the computations are taking place on the cloud, and then stage it again to some other intermediate location. However, obviously, this is not very efficient if you're running on high performance computing systems. So we also we can use this model to collocate the storage with a computational site and use parallel file systems to support the workflows executing on HPC. So obviously, if you have these distributed storage systems, we may also have different protocols with which you access the data. So we developed a tool which we call Pegasus Transfer, which is able to talk the various protocols that you see on the right. Additionally, it can also create directories and remove files. It can do two-stage file transfer. So if you have incompatible protocols, it can do the 2 stages to enable them to effectively access data in these different storage systems. It does parallel file transfers to improve performance. It can also do automatic retries, which is very useful if you have data distributed in the environment. If the first replica doesn't work, you can go and retrieve another one. And obviously, it also does credential management. So now with these 4 principles, we're able to also move to new types of deployment. So recently, a lot of applications are really going from the edge to the cloud and looking at how you enable computations both very close to where the data is being collected, but mostly lightweight computations based on the availability of computational resources close to the sensors at the edge, and then doing more heavy computations, so maybe some higher level machine learning tasks on the cloud. And some examples of these type of applications come from weather modeling. So we're working with scientists out of University of Massachusetts, which have radars in the Dallas-Fort Worth area in the US. It's an area that can have severe thunderstorms, for example. So they're using these radars to model the different project how the data will be, how the weather will be moving through that area, and potentially shut down some power and in critical areas and so forth. So they do use some computations that are close to these radars, but if they want to look at large ensembles of simulations, they might move in to the cloud. And another example is from the Ocean Observatory Initiative, where they have various sensors that are deployed in the oceans, and some of them are hydrophones that you can use to listen to orca whales, for example. So you can detect some sounds in the water, and then send also some information to the cloud to aggregate information that you hear across the ocean. So the fifth principle that really kind of clinches the whole deal. Sorry, my clicker. Okay, is this up and down integration with diverse cyber infrastructure. So as I mentioned at the beginning, we're dealing with diverse users, we're dealing with diverse applications, diverse cyber infrastructure. So we need to provide ways for users to develop their workflows in a way that's natural to them. So over the years, we supported various languages. We started with Java. We actually had some Perl as well, which we deprecated. Then we saw the bioinformatics community moving heavily towards R. So we have a R API for Pegasus. And clearly nowadays, Python and Jupyter notebooks are really what the scientists use the most. So we have those as well. However, not everybody generates their workflows individually. A lot of scientists access these technologies through portals. So we have different types of integrations with on-demand, Cybers, and HubZero. And we provide these environments with monitoring APIs so they can see what's going on with the workflows as they're being executed. In the middle, you see the Pegasus workflow management system, and in the bottom, you see all the diverse cyber infrastructure that Pegasus can run the computations on. So with these type of up and down integration with different cyber infrastructures and ways of generating the workflows, some of the applications, I can mention some of the examples of applications that use that type of setup. So one of them is the Event Horizon Telescope that I mentioned some time ago. They have an installation where they use Cybers to manage the data, the computations, and so the data and tracking what type of computations they're doing. They use Pegasus to generate a number of different simulations that you see above, basically under different conditions, different parameters, and then they check it against the data that is coming off the instruments. Another example of a collaboration that uses diverse cyber infrastructure is Xenon NT, which is a dark matter search experiment. And there they developed their own data management system. They use Rusio for data management, which is used heavily in the high performance, high energy physics community. They use MongoDB to track the instances. So really, if you want to work with these type of scientists, you need to be able to provide them interfaces to the systems that they have already in place. And another example of where this integration with different cyber infrastructure really helps is that in cases where maybe the scientists are not well versed with not only the cyber infrastructure, but also they might need to have results very quickly. So this is an example of enabling real-time feedback when the data is collected by scientists at the cryo-EM facility at USC. So as they're collecting data, they want to be able to figure out whether the data that they're collecting is of good use or should they adjust the experiment. They don't want to spend hours collecting the data, going home, looking at it, and then figuring out that something went wrong. So what happens is when they're executing when they're doing the experiment, the data is pulled into the USC HPC system. The Pegasus workflow is triggered based on the data availability. It quickly does some pre-computations. It notifies the user so that they can go in. And I think nowadays we notify them via Slack that the data is available. They quickly look at the data and decide how to proceed with experiment. So sometimes users obviously want to interact with these, not even knowing that Pegasus is inside. And that's somewhat of our problem, is if you don't know it's inside, you cannot really cite us and say, give us credit. But so another type of applications that we come across are these applications that are quite large scale. So this is an example again from astronomy. The scientists wanted to generate a galactic plane atlas that in various types of spectra. So they had 17 different spectra that they wanted to put together and make available to the community. Each of these spectra has about 18 million input images. It generates 900 output images. And the issue there is that you need to be able to, it's not a single workflow that's really going to do all this work as the individual workflows, but they're still quite large. And in addition to the fact that they're large, they reuse the same data over and over again. So for example, if you use a template for a particular type of computation, this template may be reused across the entire computation that to generate the mosaic. So I talked about the 5 principles, but in addition to the principles, we do a variety of optimizations to meet the needs of these applications. So one of them is data reuse. So for example, if you see some intermediate data products, that already are available, then the system can detect, in particular, let's say these 3 already have been computed before, the system automatically detects that, it reduces the workflow to just the components that need to be executed, and then proceeds from there. So it's basically you get more efficient computation. But also if you imagine there's something that happens during the execution, there's some failure that occurs, you don't need, even if the user gives you the original workflow, the system can figure out which part of the workflow has already executed, reduces to what's needed, and just gives you, recovers and proceeds just with the computations that need to be done. So I mentioned that a number of applications are really not single workflows, they are really collections of workflows, and this is true also of Cybershake, the application I mentioned earlier, where you have scientists generating seismic hazard maps of Southern California. Oops, sorry. And if you look on this map, each of the points on the map is an individual workflow. So we develop capabilities to manage these workflows as entire ensembles. So you can automatically spawn the workflows, you can manage them. They can be triggered by various events or fire patterns coming up on the storage systems. And you can adjust priorities. So for example, if you use this to simulate the path of a hurricane and you're using an ensemble simulation, you might want to give higher priority to the paths that you think are more likely to happen so that they'll complete faster. So, and obviously we provide different capabilities in that space that you can pause, resume the workflows, you can remove them, replan, and so forth. So this has been used successfully for the Southern California Earthquake Center. And also this application is interesting. I alluded to that earlier, that Cybershake has a mixture of high performance MPI computation. So it starts off with 3 or 4 high-level MPI codes, and then it does a lot of post-processing. So you would think that it's actually useful to then run the MPI calculations on the HPC system, and then you can run the post-processing on a high-throughput computing infrastructure such as the Open Science Grid. However, if you look at the sizes of the data that's being transferred between the simulation and the post-processing, these are quite large. So the workflows consume altogether about 120 million core hours. They're not that big, they only have 40,000 jobs, but they manage about 1.2 petabytes of data. And when they transfer data out, it's about, they downsample it to 14.4 terabytes. However, the workflow management system needs to manage the transfer between various codes and so forth, up to 157 terabytes of data. So what happens there is that even though these workloads are amenable to this heterogeneous execution on HPC systems and high throughput computing systems, you really want to keep it within one particular HPC machine. But then the question is, how do you schedule these millions of jobs that are single core on an HPC system without the administrators cutting you off, right? Or taking down the file system and the scheduler and so forth. So we developed various solutions over the years. A simple one is to do task clustering. So you cluster smaller tasks together into bigger holes. So instead of things that are running a few minutes, you run multiple hours. So already it looks a little bit better. We also use the notion of pilot jobs. So you submit a pilot job through the HPC system, and then you submit jobs directly to that pilot. So you actually go around the scheduler on the HPC machine. You can use also the combination of the two to make that happen. And then we also have developed a special workflow execution engine, which we call Pegasus MPI cluster, which basically allows us to take a chunk of a workflow and send it along with the engine to the HPC system. When they get scheduled, the workflow engine starts up, and then it orchestrates the execution of tasks through the master worker paradigm, basically assigning tasks from the workflow to the various MPI processes. So this actually works quite well, and from the point of view of HPC sysadmins, it basically looks like a giant MPI job and makes them quite happy. So another problem that over the years we have come across is that data that's within these workflows, and you saw the SCEC example, can be quite large. And so especially in the older days, we used to run out of disk space when we were running these workflows on a variety of infrastructures. So we developed technologies or algorithms that look at the workflow and then decide ahead of the execution, and then decide at which points particular data are no longer needed. And then it adds nodes to the workflow to remove that data as the workflow progresses. So we did this, we explored these algorithms on the montage workflow. As you can see from the graph, basically you have execution. This shows you how much storage the particular workflow is taking. This is execution over time. And you see as the execution progresses, the amount of storage eaten up grows. However, if you do you remove the data along the way, these are the red dots where you're doing data cleanup, you can get a significant reduction in this case, it was 125 gigabytes versus 700 megabytes reduction in the storage used. So we applied this. Montage is an easy workflow to deal with. We applied this to the LIGO workflow. And it turned out that our algorithm was not very good because the structure of the workflow, unfortunately, doesn't come off too well. The structure of the workflow is such that it brings in all the data at once. So if the workflow starts out, it brings the data and then keeps computing on it so the cleanup really is not effective. So we thought about it, and we thought, well, how about we restructure the workflow? We did it. We tried to basically break up these things into chunks and then restructure it, keeping track of the dependencies. We got a 26% improvement doing that, and then we got really ambitious, and we totally restructured it even more, and we got a 56% improvement. So with that, we went to our LIGO colleagues, we showed them, 56%, this is wonderful. And they basically looked at this monster that we created out of a nice regular workflow, and they didn't want to hear any of this, right? So this is like, they don't care because they understand on the left, they have no idea what's happening during the workflow. So, again, this went back to the case where we cannot forget about our users. We really need to listen to them, and sometimes computer science and algorithms have to take a back seat. So in general, if we work with users, oftentimes we start them off with, with drawing things on a piece of paper. So in our discussions, oftentimes we talk about, well, how does your work, what do your computations look like? What do you do? And they say, well, it's really maybe 1 or 2 steps and that's it. And we say, all right. So then we start drawing, and then it turns out, yeah, it's maybe this step and that step that they think about. But then you have all the other things that come in between. So it's really important when you work with your users to fully understand what it is that they're doing. And another thing that we have done over the past to help our users was to integrate Pegasus with a Jupyter notebook to be able to put them in an environment that they are familiar with. So now they can create workflows and monitor them and execute from the Jupyter notebook interface. And then obviously fault tolerance is also an issue when you're executing these large-scale workflows on a number of different infrastructures that have various performance and failure modes. So we did a number of different optimizations. Basically, first detecting that something went wrong. So after a job completes, we look at the exit codes. We can also do some other tricks of trying to figure out if everything went well. We can do simple job retry. So basically try it again. Maybe it will land on a different host and it will go. Sometimes also bioinformatics applications are flaky in terms of the application itself. So if you run it again, it will be better, or maybe it will land on a host that has more memory and to execute successfully. We also have rescue DAG. So if we really cannot do anything else, we give the DAG to the user to fix. And also we do file checkpointing. So as I mentioned before, you can restart the workflow from where you were. So now looking into the future, what it is that we can do better. So can we use, for example, machine learning techniques to make our system smarter? And so, yes, so you can work on anomaly detection algorithms, try to figure out if you see anomalies during the execution and potentially react to that. You can potentially classify the errors as well, so that a cyber infrastructure provider can fix what's wrong with your execution. You can do predictive models for performance, so you can figure out are you running as expected. You can also do better adaptations of workflows based on what you've detected. So these are all good promises of making our system smarter. You can also help users reuse and maybe compose the workflows better, and many other things. Obviously, when you put in the machine learning techniques into the mix, especially if you're looking at deep learning and other technologies, the issue is collecting enough data to actually feed the models. And so it's challenging to not only collect enough data, the data has to be of particular quality, it has to be labeled unless you use unsupervised learning, but you have to have enough anomaly data to really seed the models. So we have a variety of challenges associated with that. However, there are other challenges that come up when you start throwing more computing at the problem. And one of them is that we have to be mindful of the environmental cost of the computing that we're doing. So this is from a paper that was in Nature Astronomy, looking at the environmental costs in terms of CO2 emission from astronomy done in Australia. So they looked at the use of supercomputers. So that was the biggest polluter, but they compared it to the flights that the astronomers were taking compared to the observatories and the telescopes and the offices. So obviously, these were collaborations that were extremely computational heavy. And on top of that, the issue at the time with Australia is that it was using primarily fossil fuels. Now I think they're moving more into renewables, so that impact would be lessened. However, still you have to consider the amount of energy and the amount of pollution that comes from the work that we all do. And another example comes from a paper looking at particle physics experiments that actually it's being developed right now. So they looked at over time at different putting factors from the setup, the people, sorry, how much setup it would be in terms of the various experiments that they're setting up, how many people will be part of the collaboration. And then they looked at the emissions, over the years. So in the prototype phase, the digital side is taking most of the emissions, so they're probably simulating a lot of things. And then, the travel seems to be a big component, the hardware less, until you really hit the building of a full-scale instrument where the emissions will be coming from the hardware. The other thing that's interesting about this paper is that they looked, and unfortunately it kind of washes out, but they looked at, in terms of digital, what were the emission costs. And so the big costs that I found surprising were in terms of data transfer and also the data storage. So the scientists that wrote this paper basically concluded that the projects such as this have to be very mindful of what data they want to keep, how they and how much data they transmit over the networks, because that's a contributor to the emissions of projects such as this one. So we have this tension of things being more costly, and yet we need more automation. So we need to throw more computing at the problem. And as we see, our resources are becoming more heterogeneous. So we have high performance computing systems that themselves are very heterogeneous and they're increasingly faulty and complex. So they kind of look like distributed systems used to look like. Now the distributed systems have additional capabilities that then make them more programmable, but also harder to use. So you have a software-defined capabilities, programmable networks, and also very specialized data storage. And obviously you have clouds that are also a big part of what we can do for science, but they can be heterogeneous and costly as well. And not to mention all the new neuromorphic and quantum architectures that people are experimenting with. So our heterogeneity is only going to increase. So I believe that we need to have more automation. However, when we automate these things, we also need to be mindful not only about the time and budget that we put as a constraint, but also the carbon footprint as well. So in conclusion, I think, I'm hoping that we still need workflow management systems more than ever, I would say. I think the 5 principles that we developed over time, this resource independent representation, the notion of submitting locally and running globally, flexible data staging, data movement, as well as the up and down integration with the cyber infrastructure, I think still stand, and I think they'll help us moving forward. However, we have to be mindful of the users and how we present the cyber infrastructure to them. And we should improve our workflow management systems. There's still much more to do, but we need to be mindful of how we do it. So with that, I'd like to just mention that my team is hiring. So if you're a postdoc or a researcher, please come to me, talk to me after the talk. Thank you very much. And I'm happy to take questions. Scott.
I don't know how to use the mic here, but my voice is kind of loud. So what I'm wondering is, I mean, it was an excellent talk, and I saw so many parallels with research in my group. One of the things that you didn't mention that much was in reduction, different techniques to reduce how much data.
Okay, so I'm asking, can you talk a little bit about reduction in terms of if you're trying to optimize the workflow, if you can reduce from data to information, how much have you been looking into that for your workflows?
Yes, so this is not something that we do. This is what we leave in the hands of the scientists. So if they want to do reduction, we can advise them, in different compression techniques and others that they can apply. However, we don't want to touch the science or make judgment calls for them. So we let them decide how they want to reduce the data and how they want to manage it. I have a question. Yes, in the back.
Thank you. Hi, so I have a question about machine learning. So you did mention that we don't have enough data, at least for the most part, to usually adapt to the machine learning itself, algorithms. What would be, in your opinion, the best solution into compromising or integrating machine learning into the future? Because it is the future, and how do we think of ways around it in terms of putting in data, even though it's, not symbolic to what the task at hand is?
Right. So I think, we've been successful in utilizing test beds in the US. So the Chameleon test bed, which is a cloud test bed. There's also the Fabric test bed, which is a newer test bed for experimentation with networks. So I think these are very valuable for experimentation and collecting data. However, having larger scale test beds or times that you can get on machines and do some experimentation to collect the data, I think would be very useful. So, there are different data augmentation techniques that can be used as well. So we can, perturb the data in certain ways within certain parameters to hopefully also get that more data. And then using unsupervised learning can also help and try to discern whether you're working in a normal execution mode or if you're seeing some anomalies. But then it's harder also to detect what type of anomalies you're seeing. Yes, in the back.
Thank you.
It is open source. It's available on GitHub and it's open to contributions.
The spectrum of the three show that when they get us attention and it's good to
Right. So Pegasus is an end-to-end solution for scientists. So they basically apply it for the entirety of a workflow, either data coming from the instrument to through the data analysis on different environments. It can take data from instruments. It can execute things at the edge. It can also scale up and down. So if you're looking at the large scale applications such as SCEC, you can see the amount of computing and data management that you can do on behalf of these applications. So we really look at basically scalability, fault tolerance, and optimizations that we do to restructure the workflow to run on particular infrastructures. And I don't believe a solution that you're proposing would do this, but I'm happy to take it offline and talk in more detail. Yes.
Thank you. I was interested in a reflection that you made, that do not forget the user. Yes. I think that was the punchline you used. I just wanted to find out about some background information about the type of users or the demographic composition of who is working on these types of projects, and how do those factors that they have come into the project. I don't know what I'm just trying to say. It's a dynamic in our context where you can't just assume heterogeneity across the board. Different variations exist based on circumstantial issues, background issues, and those play a part in how people not only adopt but use systems. So I just wanted the background information of your
Yes.
users.
Yeah, so we started with a large collaboration, so the LIGO, the astronomy collaborations, high energy physics, but throughout the years, we've branched out to a variety of users. So we worked with PhD students, a single PhD student that needed to do genomic analysis, looking at how a certain population has migrated through Europe over time. And they didn't have the capabilities to utilize the cyber infrastructure, that they didn't know it was available. They didn't know how to use it, but we worked with them. We helped them figure out, what the workflows would look like, how you would structure them. They're able to then, we showed them how to run on Open Science Grid. And with that, they're able to then take what they had, the pieces that we gave them, the skeleton of the workflow, and then move on to the research and successfully defend the thesis. So we do have a big scale of users. However, I think a lot of our users are on the high end, but there's a big, there's some on the tail of science, but and then we have the mediums that are pretty, people that are maybe a single investigator with a graduate student, a couple graduate students that can utilize the system. And then the other thing that I think makes it viable also is through the portals that we have integrated, where Pegasus is integrated, because people don't even know that they're using Pegasus underneath, and yet they're benefiting from the workflow technologies. So this is a example from the lake modeling, for example. They go through the portals. We have people that are simulating a volcano eruption that also are going through a custom portal interface and using Pegasus underneath. So that way we have a democratization of access. Thank you. Thank you. Thank you.
Thank you very much, Dr. Deelman. Very exciting, interesting talk. I can personally vouch for Pegasus. We used it some years ago to do some processing with Earth observation data, and it really smoothed out a lot of issues that you would otherwise struggle with in terms of workflows for this kind of thing.